The universe is a vast and intriguing place. For centuries, humans have gazed at the stars, planets, and galaxies, wondering about their place in the cosmos. Our understanding of the universe and its workings has evolved over time, from ancient civilizations that worshiped the heavenly bodies, to the Renaissance era of scientific revolution, and finally to the modern age of space exploration and quantum physics. One concept that has fascinated scientists and laypeople alike is the theory of everything, a hypothetical framework that aims to explain all the physical phenomena in the universe, from the tiniest subatomic particles to the vast expanse of the cosmos. This video documentary will explore the origins, development, and implications of the theory of everything, making it accessible and understandable for everyone. Origins and development. The quest for a unified theory that can explain all the physical phenomena in the universe has been a long-standing goal of physicists. In the late 19th and early 20th centuries, scientists made significant progress in understanding the forces of nature. Sir Isaac Newton's laws of motion and law of universal gravitation, James Clerk Maxwell's equations of electromagnetism, and Albert Einstein's theory of relativity all contributed to our understanding of the natural world. However, as scientists delved deeper into the atomic and subatomic realms, they encountered phenomena that could not be explained by classical physics. This led to the development of quantum mechanics, a branch of physics that deals with the behavior of particles at the atomic and subatomic levels. In the mid-20th century, physicists developed the Standard Model of particle physics, which describes the electromagnetic, weak, and strong nuclear forces and classifies all known elementary particles. The Standard Model has been incredibly successful in explaining a wide range of phenomena and has been confirmed through numerous experiments. However, it has some limitations. For example, it does not include the force of gravity, described by Einstein's theory of general relativity. This has led physicists to search for a more comprehensive theory that can unite quantum mechanics and general relativity, a theory of everything. Attempts and challenges. Several attempts have been made to develop a theory of everything. One of the most prominent is string theory, which proposes that the fundamental building blocks of the universe are not point-like particles, but one-dimensional strings. These strings can vibrate at different frequencies, and the various vibrational modes correspond to different particles observed in nature. String theory has the potential to unify all the fundamental forces of nature, including gravity, into a single coherent framework. Another approach to the theory of everything is loop quantum gravity, which combines the principles of quantum mechanics and general relativity in a different way. It proposes that space and time are not continuous, but are made up of discrete, interconnected loops or networks. This theory also aims to unify all the fundamental forces into a single framework. Despite the progress made, developing a theory of everything has proven to be incredibly challenging. One significant obstacle is that the theories proposed so far require additional dimensions beyond the three spatial dimensions and one time dimension that we are familiar with. These extra dimensions are necessary to make the mathematics work, but they are difficult to visualize and have not been observed experimentally. Another challenge is that the theories predict the existence of particles and phenomena that have not been observed and may be beyond the reach of current experimental techniques. Implications and future prospects. If a theory of everything is successfully developed, it would have profound implications for our understanding of the universe. It would provide a unified and coherent framework for explaining all physical phenomena, from the smallest subatomic particles to the largest galaxies. It could also lead to new technological advancements, as a deeper understanding of the fundamental forces of nature could lead to novel applications. Furthermore, a theory of everything could shed light on some of the biggest mysteries in physics, such as the nature of dark matter and dark energy, which make up most of the universe but remain poorly understood. It could also provide insights into the origin and fate of the universe and the nature of space and time itself. The search for a theory of everything is one of the most ambitious and challenging endeavors in the field of physics. It represents the culmination of centuries of scientific inquiry and the desire to understand the fundamental nature of the universe. Despite the challenges faced and the questions that remain unanswered, Scientists continue to work towards this goal with dedication and optimism. While we may not yet have a complete theory of everything, the journey towards it has led to many important discoveries and a deeper understanding of the universe. It is a journey that will continue to inspire and challenge us, and one that holds the promise of revealing the ultimate secrets of the cosmos.